Okay, so you trained your artificial neuron by training your real neurons. What happened here? Again, it's easier to see if we limit it to 2 dimensions. So we have 2 input values, 2-dimensional input vector. And what the perceptron is doing is learning a linear separation between them. So in 2 dimensions, it's a line, in 3 dimensions, a plane, 4-dimension hyperplane, and so on. But it's easier to understand and visualize it when we stay in 2 or 3 dimensions. So basically, in the beginning, this function can have, well, based on the random weight settings, any kind of form. And then you'll see that some of the samples end up on the wrong side of this line. So some of them are classified correctly and others incorrectly. And by updating the weights, we are basically changing this linear function here. And then at one point, ideally, we have learned a correct linear separation between them. So you can see that this only works if the training data that we have is linearly separable. If you have input data that looks like this, then the poor perceptron will never be able to learn the correct values for all of the input values. Why? Well, there is no way to draw a line here that you get all the x's on one side and all the circles on the other side. If you put it here, you have some x's and circles on one side. If you put it here, same thing. If you put it diagonal, if you put it here, it just doesn't work. So this is an example for data that is nonlinear separable, and a single perceptron just cannot learn how to separate this kind of data. So that's an important insight into perceptrons. A famous example is the XOR function. So XOR, remember, is 1 when the 2 input values are different, otherwise it's 0. So if you draw this in 2 dimensions, 0 and 1, 0 and 1, then you can see again, there is no way to separate this with one line. If you put it here, you have an error. If you put it here, you have an error. If you put it in the middle, you have an error. So it just doesn't work. And in fact, this was mathematically proven and pointed out in a famous book by Minsky and Papert that they published in 1969. This has the somewhat unfortunate side effect that this sort of killed interest in these artificial neurons. It was part of the so-called AI winter. There were a couple of phases where AI was overhyped, and then through some over promises that didn't deliver, AI got a bad reputation, and people sort of stopped doing AI research in general and working on specific technology in particular, like here the artificial neurons. So this was one of the reasons behind the first AI winter in the 1970s. However, this is kind of like a misunderstanding. This only means that a single perceptron cannot learn this function. However, what we can do is we can combine multiple of these perceptrons together, multiple neurons together. It's a neural network, not just a single neuron. And once we have this network, we can actually learn these non-linear separable data. So how can this look like? Again, we have an input vector here, in this case 2-dimensional, and we have an output vector. In this case, it's also 2-dimensional, but it could also be 3 or 1-dimensional. And the new thing is that we now have a layer of neurons in between the input and the output layer. And whenever you have a layer in between, this is called a hidden layer. So now you just learned how to update the weights by comparing the difference between input and output. And then you would say, okay, this weight contributed so much to the error, and we're going to adjust it by this and that value. But now when you introduce this hidden layer here, it gets a lot trickier, because we don't know what the expected output from this hidden layer is. We know the expected output here, but we don't know the expected output here. So we can't really say how much do we have to adjust these weights here. So the algorithm that was proposed later on, and that is sort of still being used with some modifications, is the idea of backpropagation. It was first proposed around the same time, late 1960s, but it wasn't really widely used on large-scale data sets until the 80s, because as you'll see, you have to do a lot of calculations and you need powerful enough computers to do it. So the core idea is the same as before. It's supervised learning. We provide some input to the network. We compute the output. We determine the error, and we want to be able to adjust the weights to reduce the error. And because we now have a network, this is done in 2 steps. So the first step is applying the input. We compute the activation. We get the first output values here, and then we repeat it. So this is the feed-forward phase. We propagate the values until we arrive at the output layer. And now there is a backward step. This is where the backpropagation comes in. So at the output layer, we compute the error, and then I'll show you how this is done. And then we adjust the weights backwards. So we first adjust the weights here, and then we adjust the weights there until we come back to the input layer. So first, the output step. This works just like before. First, we have this weighted sum, just like in the Perceptron. The only difference here is that we don't use this step activation function. We're going to use a sigmoid activation function. Later on, you'll see people use lots of different activation functions in these networks. They have various advantages and disadvantages, but this is one of the classic ones used in the original backpropagation idea. So again, this is how to decide based on the input x here, which is the weighted sum, just like before, what do we compute as the output? So it's not going to be just 0 and 1, it's going to be a value in between. So now how do we update the weights? This is where it gets a bit mathematical, and I'm not going to show you the math here. If you take a machine learning course, then you'll go through this in detail. The core idea is that we want to look at the gradient of the loss function, and we want to adjust the weights so that we get towards an area of a smaller error. It's easier to see on an example. So let's say we have 2 weights, again, to be able to visualize it. And now with these 2 weights, we can give them different values, like you have done. You adjusted the weights. And now, given a certain combination of weight 1 and weight 2, we can compute an error function. So this is just, for example, how many of the input samples were misclassified. So if given 2 weights, we misclassify a lot, we are going to have a high error. If based on 2 weights, we don't make many mistakes, ideally, we have an error of 0. So now we are going to start by initializing these 2 weights, for example, some random value, and we are somewhere here on this error curve, on this error surface. And now we want to be able to change the weights. And we want to be able to change them so that the error becomes smaller. So you can see on this function here, we want to go towards a decreasing value. We're taking steps, we're adjusting each weights down this error curve until we arrived at the point where every change would only make it bigger. So this is the idea of gradient descent. We're computing the derivative of the function and then go towards the direction of a smaller error. So here, this is a very simple and nice error curve. In a real-world problem, it's going to look a lot more complex, especially not just convex, it's also going to be non-convex. And you can see that depending on where you start on this error surface, you have different end results. If we start here, we're going to update the weights. It's getting better and better and better. But now we are sort of in a local minimum. No matter what we do, we're not going to be able to decrease the error. We're sort of stuck here. If, on the other hand, we have this initial weight here, we can come to a much better end result with a much lower error. So you can see two things on this error curve. First, you understand why these weights are initialized randomly. Now, if you would always start in the same place, there might be a good chance that you never find the optimal solution because you're getting stuck in a local minimum somewhere. So this is why these weights are initialized randomly. And you can also see that typically you run the neural network training multiple times because, again, with one initial weight, you are not necessarily to get the best output. So you repeat it with multiple different initial weight settings. So the whole math between it, we're not going to cover in this course. Again, if you take a machine learning course, you're going to learn it. And if you're interested, the references for this lecture, you can look at the calculations. It's not really that difficult in terms of math. So it's not that hard to understand. It just takes a lot of time to go step by step through these calculations. So I would need almost a whole lecture just to go through it in detail. And yeah, in this course, we're going to do different things. So here we're focusing mostly on applying this to various real-world problems, like writing chatbots and other intelligent system applications. So we're going to simply use existing libraries. One library that's well known for building these modern type neural networks is Keras. Originally, the idea of Keras was that you have a nice Python API as a front end, and then as the back end, you could use different libraries. And there are, as you can guess, dozens of different neural network libraries around. So if you wanted to experiment with different libraries, but not change your code all the time, just to use a different backend, the idea of Keras was that you can stay with the same front end, and then you configure different backends. Now this has changed for reasons that I'll explain in a minute, but now the current version of Keras only works with one framework, and it's directly integrated with the framework, which is TensorFlow. So I guess everybody has heard of TensorFlow. This is the open source machine learning library that comes out of Google. And this is nowadays one of the two major libraries that's being used, the other one being PyTorch. As you can guess from the name, PyTorch is again a Python library. Originally, it was a Python interface for the Torch library, but nowadays all the development has shifted to the PyTorch project. So where TensorFlow comes out of Google, PyTorch is again an open source project and comes from Facebook research. So the state of the current art is that most of the work has consolidated around these two libraries. Now there used to be dozens of these machine learning, neural network, deep learning libraries, but because both Google and Facebook have been throwing so much money into their libraries that all the others basically couldn't really keep up. And most people nowadays are using either PyTorch or TensorFlow. So let's look at how you could build a neural network in Keras. So you can see the workflow is very similar to machine learning that you have done in scikit-learn. Yeah, we're going to import the neural network from Keras. We're going to load our dataset, and in this case, we're using a diabetes dataset. So that's the p-Meridians diabetes dataset. Basically, we want to predict if someone is getting diabetes based on a number of diagnostic measures, like some blood values and so on. So just like before, we have our input vector, and then the output vector. Now we define a sequential model, which is a feed-forward neural network, like you've just seen in a diagram. So we define how many neurons there are in the input layer, the hidden layer, and the output layer. We define the activation function. So here we're going to use another one that I haven't shown you yet, which is called ReLU. But again, it's just another type of activation function. And you compile this model. And then just like before in scikit-learn, you do a training by saying fit on X and Y. Then you define how many of these epochs you want. In this case, we do 150. And batch size means after how many training samples we do an update of the weights. So far, we have always updated after each weight, but there are different strategies updating after a certain number of input values. So this one here I took from an example that you can download and also try out. This is a very simple network. You don't need any fancy hardware to be able to train and run this. So when you run it, you can see it's going to go through all of these epochs, and in each epoch, we go through all of the 768 training samples. And we can compute the loss error function and the accuracy that we have. So after one epoch, just like you've done on the worksheet for the simple Perceptron, we have an accuracy of 61%. And then we continue and continue. And you can see after 150 epochs, we increased this by almost 10%, from 61 to 70.9%. Okay, now you know some basics on neural networks, which is enough to get us started with what we really want to do, these word embeddings that I talked about in the beginning. See you then.